Welcome to this explainer. The environment around you right now might seem perfectly still, but it is absolutely saturated with complex, invisible forces. Today, we're unpacking the mechanics of wave and electromagnetic theory. And look, understanding these dynamics isn't just some academic exercise anymore. It's literally the fundamental basis for everything from our global telecommunications to quantum computing. When we actually grasp how these forces propagate and transfer energy, we uncover the hidden infrastructure of our entire modern technological world. It's like a giant puzzle, and we're about to put the pieces together.
Okay, let's dive into this. Here is our roadmap for today. We're going to start with the anatomy of waves, then we'll compare light versus sound, move into bending and bouncing waves, and finally, look at how waves power our everyday life. We're building from the micro concepts all the way to the macro applications.
All right, part 1, the anatomy of waves, building our toolkit. We're going to run through the fundamental stats of a wave in a quick rapid-fire sequence here, so stay with me. First up, frequency. This is the number of wave cycles that pass a specific point in a given amount of time. Think of it like the core pulse of our invisible mechanics. Beyond just setting a basic tempo, frequency directly indicates a wave's quantum energy state. Thanks to Planck's relation, where energy equals Planck's constant times frequency, we know that a higher frequency inherently means a higher energy photon. In the real world, manipulating these high-frequency states is a real game changer. It lets us execute advanced data multiplexing, packing massive amounts of digital info into super-compressed signals that zip across the globe in literal milliseconds.
Next, we have wavelength. This is the actual physical distance between two consecutive corresponding points on a wave, like from one peak to the next peak. But it's way more than just a measurement of space. It dictates exactly how a wave is going to interact with matter. For instance, long radio waves have wavelengths that can stretch for meters or even kilometers. That lets them effortlessly bend around obstacles and pass right through solid concrete building walls. But in stark contrast, the super short wavelengths of visible light interact really strongly with atomic structures, which is exactly why visible light can't penetrate those very same walls.
Moving right along to period. This is the amount of time it takes for one complete wave cycle to pass. So while wavelength is space-based, period is time-based. The two are intimately connected through a strict inverse mathematical relationship. Period is simply 1 divided by the frequency. So if a wave completes 10 cycles per second, its period is precisely 1/10 of a second. Understanding this inverse relationship is absolutely crucial if you're an engineer designing oscillatory circuits or fine-tuning a radar system, because calculating the exact time delay between sent and received pulses makes or breaks the accuracy of the whole system.
Okay, amplitude. This is the maximum displacement of a wave from its resting or equilibrium position. Instead of just picturing this as the size or the height of a wave, you've really got to view amplitude through the lens of pure power. In physics, the energy a wave transports is directly proportional to the square of its amplitude. That means if you double the amplitude of a wave, you don't just double its energy, you quadruple it. No way around it. This exponential scaling is exactly why even slight increases in the amplitude of seismic waves result in exponentially more destructive tectonic events.
Then there's velocity, which measures the speed at which a wave propagates through a medium. It's the critical measure of how fast this energy moves from point A to point B. Now, a mechanical wave's velocity fluctuates wildly depending on the density and elasticity of the material it's traveling through. But the velocity of an electromagnetic wave in a vacuum? Well, that introduces us to a foundational constant of the universe. I'm talking about the speed of light, denoted as c, clocking in at nearly 300 million meters per second. It acts as the ultimate cosmic speed limit, fundamentally linking space and time.
Finally, energy. This is the capacity of the wave to cause physical change or perform work. This is the ultimate synthesis of our entire toolkit. When you combine frequency, wavelength, period, amplitude, and velocity, you define the wave's total capacity to alter its environment. Whether it's a super high-energy gamma ray with the sheer power to strip electrons right off atoms, or a low-energy radio wave just gently nudging the electrons in your car's antenna, these metrics precisely calculate the total energy output of the invisible forces moving through our universe.
Section 2. Light versus sound. The Great Divide. Let's move to and see how this builds into an epic head-to-head battle between two key forces in physics.
So we have this fundamental divide between mechanical waves, like sound, and electromagnetic waves, like light. Sound is mechanically dependent. It propagates by physically colliding particles together, which means it completely requires a physical medium, like a gas, liquid, or solid, to transfer energy. On the flip side, light requires absolutely zero physical medium. An electromagnetic wave propagates by generating oscillating electric and magnetic fields that continuously regenerate each other. It's the self-sustaining interplay that allows light to travel through the absolute vacuum of deep space, delivering energy from distant galaxies straight to our observatories.
Now, what's really interesting about this slide is how those 6 toolkit stats we just learned behave completely differently in light versus sound. Because sound is mechanical, its velocity is incredibly sensitive to environmental factors like temperature or the density of the material it's in. Light, totally unhindered by a medium, outpaces it by orders of magnitude. This huge variance is exactly why you see a lightning strike seconds before you ever hear the thunder, and we actively exploit this divide. Systems like sonar rely on the predictable speeds of sound waves through water to map the ocean floor, while radar systems use the near-instantaneous bounce-back of high-frequency electromagnetic waves to track high-speed aircraft in the sky.
Section 3. Bending and bouncing waves, the rules of movement. Let's explore the physical rules that dictate how these waves interact with the environment around them. We need to compare bouncing versus bending. Reflection happens when a wave encounters a boundary it just cannot penetrate, so it bounces back. This is strictly governed by the law of reflection, which tells us that the angle of incidence exactly equals the angle of reflection. Refraction, however, is a different story. This involves the wave transmitting entirely into a new medium, and as it crosses that boundary, the change in the new medium's properties causes the wave's velocity to shift. That physical shift literally alters the wave's trajectory, bending it right away from its original path. To picture this, think about a highly relatable everyday mystery. Why does a straw look broken or disjointed when you drop it into a glass of water? Well, this visual shift is completely driven by optical density. Water is optically denser than air. So, as the light wave reflects off the submerged part of the straw and exits the water into the air, it abruptly accelerates because the optical density decreases. That acceleration causes the light to bend away from its original path before it even reaches our eyes, creating the crazy illusion that the solid straw has been snapped in half.
And that broken straw brings us right to Snell's law. This is the mathematical model used to describe that exact relationship between the angles of incidence and refraction. But rather than just being a dry geometric formula, Snell's law introduces the refractive index, a number describing exactly how fast light travels through a specific material. By comparing the refractive indices of 2 different media, engineers and physicists can calculate precisely how much a wave is going to bend. This exact predictability is literally the foundation for how we design complex optical lenses, microscopes, and telescopes.
Section 4. Waves in everyday life, the real world. And this brilliantly illustrates how we bring abstract physics down to the practical technology we rely on daily.
Our everyday instruments are really just sophisticated transmitters or detectors of specific wave frequencies. I mean, consider the actual device you are using to watch this explainer right now. Your screen is emitting highly specific wavelengths of electromagnetic radiation, photons. These photons are traveling through the air, hitting the cornea of your eye, refracting through the lens, and precisely focusing onto your retina. Your biological optical sensors then convert that electromagnetic energy into electrical signals for your brain to decode. You are actively participating in an incredibly complex exchange of wave mechanics right this second, just by processing my words.
So the crucial point is that understanding and mastering these invisible forces is genuinely what makes our modern world possible. Beyond just the devices in our hands, our entire global internet infrastructure relies on these principles. Fiber optic cables, the ones spanning the ocean floors, use a phenomenon called total internal reflection. By calculating exact angles of incidence, lasers pulse billions of light waves per second through strands of glass, bouncing them internally without any signal loss at all. We've essentially trapped electromagnetic energy and used its incredible velocity to transmit human knowledge across the planet in milliseconds. It's absolutely mind-blowing.
So I'll leave you with this. What invisible waves are transmitting through your room at this very moment, and what immense amounts of data are they carrying? You are currently immersed in a complex, overlapping ocean of invisible energy. From the cosmic microwave background radiation left over from the early universe to the tightly encoded cellular signals connecting you to global networks, these forces are constantly vibrating around and through you right now. Thank you so much for joining me on this explainer. Keep observing, keep questioning, and I'll catch you on the next wave.